Welcome to the practical session. That is experiment number 9. We have to write the program to design and implement the IR filter using Butterworth or Chebyshev approximation. In last video we have already covered the Butterworth approximation, and in this video we have to go with the Chebyshev approximation. So for this purpose, here we are going to consider the problem statement, and that is design a Chebyshev IR low pass filter to satisfy the following constraints. That is passband is 0.707 is less than or equal to mod of h of omega is less than or equal to omega. So this is the passband, and over the range, that is from 0 is less than or equal to omega is less than or equal to 0.2 pi. So 0.2 pi is the passband frequency, and here mod of h of omega is less than or equal to 0.1. So this is about the stop band magnitude response, and here it is 0.5 is less than or equal to omega is less than or equal to pi. So my stop band frequency is 0.5 pi. And here we have to use the bilinear transformation, and with sampling period t is equal to 1 second. So here it is provided with A1, A2 and passband frequency omega 1 and stop band frequency omega 2. So this A1 and A2 is there in you may say in value, that is 0.707 and 0.1, and it can be converted into the decibel values, and those decibel values can also be used in MATLAB also. So this A1 and A2, these are the passband and stop band gains, one can say. Here as per the Chebyshev approximation, here we need to consider first the ratio of analog frequencies. So first of all, we need to convert our analog digital frequencies into analog one by using bilinear transformation. So for that purpose, we are going to use the ohm to, that is the ratio of passband and stop band, that is ohm 2 upon ohm 1 is equal to 2 by t tan of omega 2 upon 2 divided by 2 by t tan of omega 1 upon 2, where this omega 2 and omega 1 are well mentioned in the problem statement. So once I know the analog frequencies ratio, one can calculate the order of filter, that is directly from using the standard equation. So n is greater than or equal to cos inverse of 1 by epsilon in square bracket 1 by a2 square minus half raised to 1 by 2 divided by cos inverse of ratio of analog frequencies. This is done in MATLAB automatically, that we will see. Once I know the order, next task is we need to determine the cutoff frequency as that of the Butterworth filter also. So ohm c is equal to ohm 1 divided by 1 by a1 square minus 1 raised to 1 upon 2n. So this gives me the cutoff frequency. Once I know the cutoff frequency, the next task is we have to determine the transfer function of analog filter. So this transfer function in this case is given by HA of S is equal to multiplication of the terms over the range k will range from 1 to n by 2 bk ohm c square upon a square plus b suffix k ohm cs plus c suffix k ohm c square, and here you need to calculate all these terms from the analytical solution, that is equal to b1 ohm c square upon a square plus b1 ohm cs plus c1 ohm c square. Here b1, capital B1 and small b1 are need to be calculated, and c1 it's also calculated from the analytical terms which are mentioned in the solution. So one can have directly the transfer function, that is HA of S is equal to 0.211 divided by s square plus 0.4181 s plus 0.2985. So by following all these steps in Chebyshev, we are having the transfer function, that is HA of S is equal to 0.2111 divided by s square plus 0.4181 s plus 0.2985. So here it is observed that the order of analog filter is the second order, and once we have the analog transfer function, one can convert it into the digital one by using bilinear transformation, that is h of z is equal to HA of S, that is equal to S is equal to 2 by t 1 minus z inverse upon 1 plus z inverse. So replace small s by this right hand side, that is 2 by t 1 minus z inverse upon 1 plus z inverse, and assume t is equal to 1 second. So by solving this, we can have the transfer function h of z is equal to 0.0411 1 plus z inverse bracket square divided by 1 minus 1.414 1 minus 1.441 z inverse plus 0.6744 z raised to minus 2. So this is about the low pass filter, and by using Chebyshev approximation and for the infinite impulse response case. So here we can verify our solution by using MATLAB. So for that purpose we have written the MATLAB code over here, and here the problem statement is we have to determine the IR filters transfer function to satisfy the following constraints, and these constraints can also be considered in terms of equivalent decibel values. So one can have the second problem statement also. So here I am going to use this second problem statement, which is equivalent to this first one, and here I am going to design the IR filters by using Chebyshev approximation. And note down, here we are using the Chebyshev type 1 filter. So in MATLAB we have written about the MATLAB initialization, that is CLC, close all, clear all, and clear figure file. And here we have just entered the specifications of the given analog filter. So here I am going to use the variables, that is omega p for passband frequency, omega s for stopband frequency, capital T for sampling period, then a suffix p for the passband attenuation gain, and a suffix s stopband attenuation gain in decibel values. So here these are the 4 specifications that we can enter. And once I know these 4 specifications by using the standard command in MATLAB, that is Chebyshev type 1 filter. So for that I can use the Cheb1 ORD in bracket passband frequency, stopband frequency, passband attenuation, stopband attenuation, and obviously it is for the analog domain, so single quote S. So this command will provides me the order of filter and cutoff frequency. Once I know the order of filter and cutoff frequency, I can convert this required specification into the transfer function, which is nothing but the numerator and denominator coefficients, that is small b and a. One can calculate by using the commands, that is Chebyshev type 1. So Cheb1 in bracket the filter with capital N order, and filter with the passband attenuation and the passband frequency. Once we provide these details, these specifications, we can have the numerator coefficients and denominator coefficients, and that can be converted into the display form, that is the transfer function. So HA of S is equal to transfer function of numerator coefficients comma denominator coefficients. So this is the analog filter, that is line number 37. It can be converted into equivalent digital filter simply by using the bilinear transformation as that of the Butterworth case. So numerator D, denominator D, bilinear of b comma a comma 1 by t. So this particular line number 39 will calculate the digital filters transfer function simply by replacing small s by 1 by t, 1 minus z inverse upon 1 plus z inverse. So once I know the transfer function of digital filter, next task is we need to calculate the frequency response of the digital filter. So for that purpose we need to convert our analog frequencies, digital frequencies into an equivalent analog values, that is passband and stopband, that is obtained by using the 2 by t tan of by using the bilinear transformation. One can have the digital passband edge frequencies and digital stopband edge frequencies from the formula, that is 2 times tan inverse of WP into T upon 2. So this is the standard equation that is there in terms of bilinear transformation, and here we have to consider the frequency range, that is from 0 to pi. And once I know the frequency and once I know the numerator and denominator coefficients, I can go with the standard command, that is h of omega is equal to frequency z of numerator d comma denominator d comma omega. And once I know the h of omega, I can split that h of omega as a magnitude function and phase function, and I can plot it with respect to the omega value. So for that purpose I have used the subplot command, subplot of 2 comma 1 comma 1, plot of normalized frequency, that is w by pi, or here you may say omega by pi, comma magnitude, and it is in red color, and subplot 2 comma 1 comma 2, a plot of normalized frequency value, that is omega upon pi, comma phase in green color, and grade on here x label, y label, title, all these things are known to you already. So these are the standard commands that we have used. So once I run this code, the MATLAB will ask me to enter the passband frequency. So my passband frequency is 0.2 pi, stopband frequency is 0.5 pi, the sampling period is equal to 1 second, the passband attenuation is 2.7 dB, and the minimum stop band attenuation is about 20 dB. So these are the values that we can convert from the given specification. So in AP and in AS, it can be considered in decibel value rather than the gain value. So they are converted into a decibel one, and that decibel values are used over here. That is 2.7 and 20 dB. So here I am getting the order of filter is 2 and the cutoff frequency is 0.6283. So for these two specification, my Chebyshev type 1 filter will be have the transfer function that is 0.2126 s square plus 0.4306 s plus 0.2901. So this HA of s is nothing but the transfer function of the another filter that we are getting at this point, that is HA of s is equal to 0.211 divided by s square plus 0.4181 s plus 0.2985. So if I observe the MATLAB solution, this is analogous to, or it is near, this transfer function is near about the HA of s that we are having in analytical form. So here in final step, I can convert this HA of s into H of z simply by using the bilinear transformation. So this is the expected transfer function that I should get in MATLAB. So if I observe this MATLAB solution and my analytical solution, they are matching with more than 99% accuracy. So here I am having 0.0411, and here I may have z plus 1 bracket square, so z square plus 2z plus 1. So if I multiply it with, I am having the transfer function h of z is equal to 0.04127 z square plus 0.08254 z plus 0.04127. So this is about 5 decimal after 0 point divided by z square minus 1.44 z plus 0.6656. So this is about the digital transfer function of Chebyshev low pass filter, and here one can calculate the passband and stop band frequencies by using the bilinear transformation. So if I observe the figure 5, here I am having the low pass filter, and that is of type 1. So it has a spike, or you may say the peak, or you may say the ripples in passband rather than the stop band. So this is the type 1 filter, and here we are having the magnitude and phase response with respect to omega, and this frequency is considered as a normalized value. So normalized value means pi divided by pi, so it is 1, and 0 divided by pi, it is 0. So here the frequency values are considered in normalized terms, that is omega divided by pi. So if my frequency is pi, then pi divided by pi, it will be 1. So it is a ratio of simply the same number. So this is about the magnitude and phase response by using MATLAB and for the Chebyshev type 1 filter. So this is Santosh Lukare signing off.